Welcome back, everyone. This is Dr. Gallenstein, and here we are again with an RStudio demo, this time for Lecture 11. So in Lecture 11, we talked about propensity score matching. Propensity score matching is one of those tools that we can use to identify causation, even if we don't have the luxury of randomization. So let's jump into R, and let's just see how can we use commands in R to perform propensity score matching. Okay, so of course, we'll start off just by activating a couple of packages that we might need to use. I will point out a particular one here called Matchit. Matchit will need propensity score matching. That will give us one of the commands. So if you do not already have that, go ahead and also install it. Install Matchit. Go to Install Packages and install Matchit. Okay, and then import the data set. I'm going to use this wages underscore PSM data set. And I'm just going to give it the name wages, as I have done in most of these lectures. So now that we have our data, we can take a look at it. In this data set, again, we have wages, we have a number of individual characteristics, and what we're going to do in this, or using this data set, is we're trying to analyze the impact of some training that these individuals received on their wages. We want to know, does this particular training increase their wages? And so we have this variable here called training. It equals 1 if they've received the training, 0 otherwise. And I have two versions of this training just so that I can kind of show you a couple different, just kind of illustrate it using two different options for that training variable. Okay, but the basic idea here is that we want to know, we want to measure the impact of the training on wages. We want to know what's the causal impact, I'm going to say causal impact, or the causal effect of the training on wages. All right, so we're going to use propensity score matching today. Let's see how that works. So first, when we're doing propensity score matching, basically, we use propensity score matching if this training, in our case today, if the training is not randomly assigned, because then the variable that indicates who received the training and who didn't is not going to have statistical independence. So now, one thing we might do to just check that or kind of confirm that our intuition is correct, we could do a balancing test. Now, if training were randomly assigned, then we would expect that a balancing test would come out to be insignificant. That means all these t-tests would be insignificant. But because the training was not randomly assigned, I have no reason to think that the sample will balance. So I don't think this will balance, and if it doesn't, that'll kind of confirm the concern. It'll confirm the concern that training, that if we try to measure the impact of the training, that we'll have omitted variable bias. So let's see. All right, so looking at some of these, all right, this one's highly significant. One's highly significant. Okay, that one's not. This is highly significant. This is highly significant. Okay, so these two samples are very different. The people that are that receive the training are very different on average from the people that didn't receive the training. And so we will have omitted variable bias if we try to analyze the impact of the training using a standard OLS regression model as we've done in the past. So we need to solve that. So that's the problem. We have a clear problem. Training is not statistically independent, and so we will have omitted variable bias. So now we have to try to solve that problem. Now the way we're going to try to solve it is we're going to try to solve it using propensity score matching. Okay, so the idea behind propensity score matching is that we will try to take people in the treatment group and match them to people in the control group, so that we will have a group of people in the treatment and in the control who are similar on average. We're going to try to find the subset within our data where the control group and the treatment group are comparable. We can see that on average in the total data set, they are not comparable. Well, what we're going to try to do with PSM is try to match treatment people to control people so that we can create samples that are comparable. Then that will mimic or imitate randomization and will allow us to get that causal identification. All right, so that's what we're going to do with PSM. PSM has two assumptions. The first assumption is that the assignment of the intervention, and what I mean by that is who receives the training, is determined entirely by observable characteristics, by characteristics that are observable in our data set. Okay, that's the first assumption. We can't validate that one empirically. We can't validate that one using data, so we have to use our intuition for that, which I talked about in the lecture. The other assumption is what's called the common support assumption. The common support assumption says that there really are people in the treatment group and control group that are similar to one another. That there are people in the control group that can serve as a valid counterfactual to those that are in the treatment group. Okay, that they are comparable. Okay, so that's the common support assumption. There's enough people that are comparable between the treatment group and the control group. So we can validate that one empirically, so I'll show you how to do that here. Okay, so the idea behind the propensity score matching is what we do is we actually run a Probit regression model where we use the treatment variable, in this case training, as the dependent variable, and we regress that treatment variable onto a bunch of the other individual characteristics. The goal here is that we want to generate a model, or we want to fit a model that will generate a predicted probability that any person might be in the treatment group. That is, the predicted probability that the person would receive the training. And that predicted probability is what we call the P-score, the propensity score. And we will use the propensity score as the basis for our matching. So let's run a Probit model where I have the training variable as the dependent variable and then a bunch of independent variables. We've seen this notation before, so I won't walk through it, but it's basically we're just running a Probit model. So I'm going to run that. Here are the results of our Probit model. Okay, great. I don't need to interpret these coefficients right now, so I won't calculate the marginal effects. If I did want to interpret the coefficients, then I would need to calculate the marginal effects. You can find that, how to do that, in lecture number 8. All right, so now to get the propensity score, I will generate the predicted value from this model. So I'll just run that here. I'm going to call it P-score. And I'm going to create that as a variable in the wages data set. So let's do that. And so now I should have that in my wages data set. Let's take a look at it. Here's our P-score. That P-score gives us the probability measured at each individual, for each individual, the probability that they are in the treatment group. That is, the probability that they received the training. Okay. All right, so now what I'm going to do to evaluate this common support is I just want to graph it. I'm going to graph that propensity score, and I'm going to graph it separately for those that are in the treatment group and for those that are in the control group. And what I'm looking for is I am looking for whether or not there's significant overlap in that propensity score. So that's what we're going to do. Let's take a look at that. Now here's the code for it. I want to create a plot. All right, I'm given the name of that plot, just PL for plot. I'm using the ggplot command. I have to specify the data set, so I'm using the wages data. I got to specify what variable I'm using within the wages data set. That's under the aesthetics, or AES. And I want the P-score. In R, I'm going to go ahead and use a histogram. So I'll do plus geom histogram. And then I'm going to do something kind of interesting here. You'll see what this means in just a second. But I'm using this AES command again, and then fill equals factor training. What this code here does is it tells R that I want it to plot a histogram of the P-score variable, but I want it to plot it separately for the treatment group and the control group. That is, separately for those for whom the training variable equals 1 and for whom the training variable equals 0. So it's going to plot them both on the same plot, but it's going to show them in different colors so we can see them and compare them. Okay. Don't worry about this alpha right now, although I would recommend including it. what it does is it makes the bars in the histogram transparent. It just helps visualization. All right, and we're going to give it an X label, label the X-axis with propensity score. So let's generate this. You can see, okay, so there is our histogram. All right, now by looking at this histogram, we can get an idea for the common support. Okay, so here, I mentioned before in the histogram command, I gave it this aesthetics fill equals factor training. What that line of code does is when we plot out the histogram, it plots out in different colors the histogram for the control group, for which training equals 0, and for the treatment group for which training equals 1. So now you can see that we've got two different histograms in different colors superimposed on each other, and we can compare them. So when we look at this, we can see there's some overlap, especially in this area here. There's some overlap, very little overlap for most of, or for a great deal of the space. And we can see that the majority of the density for the control group is way down here near 0, and the majority of the density for the treatment group is up here near 1. So when I would look at this, I would say this doesn't look good. This is a little bit of a judgment call, but looking at this, I would say there is very little common support here, and propensity score matching might not be the right approach in this case. So that would be my assessment here. Now, just for the purposes of illustration, as I showed you before in the wages data set, I have two different training variables. I've just created those two different variables so I can show you what it looks like using two different ones. So let's generate the p-score using this training variable 2. Let's imagine this training variable 2 was the actual training variable. We'll generate the p-score for that. I'm just calling it p-score 2. Okay, and then let's generate the plot, same plot. But for this one, and see, okay, here we go. So here's the propensity score. We've got the propensity score for the treatment group in blue, propensity score for the control group in red, or pink. And you can see that there is very heavy overlap here. These two groups, these two samples are very, very similar to each other. So just from looking at this, I'm just kind of giving you a comparison between what is a pretty bad common support here, where the majority of the density is separated from each other, versus like a crazy strong common support where the two samples really just overlap with each other. So I want to show you that so you have an idea for how to distinguish what is and what is not good evidence for common support. Okay, so there we go. There's validating the common support. Now let's go ahead and perform the matching. I'm going to use the training variable. I showed you that I had 2 in there. At home, go ahead and recreate this for training 2 and see what you think of it, but I'm just going to do it here for training 1. Even though this training variable didn't really pass the validation for the common support, but I'm just going to show you the steps. Okay, so here we go. The idea of what we're doing here is we are actually going to use an R command called matchit. We loaded that library and installed it earlier. We're going to use this command matchit to, in the data set, match treatment observations to control observations. Okay, so we're going to do that right here using this matchit command. All right, I'm going to call this matching. All right, and then I'm going to use the matchit command. Inside the matchit command, what I do is I put in the model for my propensity score. So do training regressed on whatever independent variables I want. I specify the data set. I specify the method. Here we're going to use nearest or nearest neighbor. And then a couple other things. It's important to put these in here, but I won't necessarily talk about what those options are. So let's go ahead and run that. Okay, so what this has done is it's performed a matching, and here's some summary information about the matching. This shows us the summary of the number of observations in the control and in the treatment that fall into different categories. So which ones were matched, which ones weren't matched, which ones were discarded, etc. Okay, so then what we want to do is we want to create a new data set that includes only the data that was matched. And so what we're going to do here is we're going to do wages.match. That's just going to be the name of my new data set. And I'm going to use this match.data command to generate the matched data. So here I'll run this and we'll take a look at it. So here I have my original wages data set here, and I have a new wages data set. And this new wages data set includes only the observations that were successfully matched. Only the observations that were successfully matched. Okay. So there's only 156 observations here instead of 526. The reason there's so many fewer observations is because this data set includes only the data where there was a successful match. All right, and this makes sense. So when we look at this, we can see that we lost quite a bit of sample size. We went from having 526 observations down to having 156 observations. That was a lot of data lost. Well, why did that happen? Well, here is our common support plot for this training variable, and we can see there is very little overlap. There's very little common support, and so it's not surprising to us that such a small number of observations were able to be matched. Now, this is kind of, again, the reason why propensity score matching, why we need to have a strong common support, because if we don't have a strong common support, we're going to lose tons of data because there just isn't a lot of comparability. So anyways, here's our matched data. This is all the information that is matched. So now, once we have our matched data set, how do we generate our estimate of the treatment effect? Well, there's two ways we can do it. One way is to just do a mean t-test for our outcome variable, wage, between those that received the training and those that did not receive the training. All right, so we've seen the t-test command here before, so just repeating that. But take note that we're using the matched data set and not the original data set, right? Okay, so we're going to use a t-test using the matched data set. And so here's that result. So we can see here that the mean difference is statistically significant, and so that would give us the indication that that there is a statistically significant difference. And then if we want to know what's the size of that difference, we would just we would have to calculate by hand the difference between the two groups. So here's the wage for the treatment group, here's the wage for the control group in the matched sample, of course. So we would just subtract, we would just find the difference between these two, and that would be the impact, and then that impact is statistically significant based on the p-value. Okay, so that's one way of doing it. We can just use a mean t-test in the matched sample. So that's one option. Another option that I actually didn't talk about in the other lecture, but something we can do, is we can run a regression, just standard ordinary least squares regression, using the matched data set. And so what we can do here is we can use the linear model command, regress wage on training and the other independent variables that we want. But here, instead of using the wages data set, we're going to use the wages.match data set. So we're basically running a regression using only the data where there was a match. And we can report those results. You can note here that I'm reporting results with robust standard errors. And so here we can get an estimate of the treatment effect. So here, the treatment effect, we can see highly significant, and we find an impact of 5.67. Okay. We can see there's a little bit of a difference between this and the mean t-test. That's probably because we have other control variables in the model. Okay, so there's two different ways we can do it to get that estimate of the treatment effect. Now, one last thing I'll do is that one thing that you might do to kind of validate the methodology, the propensity score methodology here, is you might do a t-test, kind of rerun your balancing test, using the matched data. And if the t-test comes out and none of the t-tests are statistically significant, or at least no more than 1 out of 10 is significant at the 10% level, then that would be a nice kind of confirmation that the methodology looks good. If that does not come out, that would raise red flags that that propensity score matching is not going to work in this case. So we can do that here. Let me just take a look real quick. We say this one is not statistically significant. This one is. This one isn't. This one is. This one isn't. So when we look at this, we can see that there's at least better balance than there was before we did the matching. But there is actually still significant difference between the treatment group and the control group even after we've done the match. And so having done this balancing test, it doesn't look good. Honestly, if we saw this result, we would say, okay, propensity score matching didn't work in this case, and we do not have a causal estimate. The samples are still not comparable even after the matching. Now you might ask, why is that the case? How could it be that we would do this matching and the two groups would still not be comparable? They are more comparable, but they're still not comparable. We can see 2 out of 5 are statistically significant. There's a statistically significant difference for 2 out of 5 variables. Why is that the case? Why didn't matching solve it? Well, one important reason, again, is this common support. We can see that there's very little comparability between the treatment group and the control group. So when R goes and it does this matching technique, it's trying to match treatment people to control people, and there are just very few people to compare to because there's very little overlap. And so propensity score matching is just not going to work when those assumptions don't hold. So we can see that we have very weak common support here, and so it's not terribly surprising that our assumptions don't hold, and therefore it's not terribly surprising that even though we've done the matching, the samples are still not comparable, and therefore we cannot conclude causation. Our estimates of the causal impact are not causal. Okay, so that's it for today. I hope you enjoyed the lecture, and I will see you next time.